Chiều nay nghỉ. Nào.
How are we doing? Fine. How was the work? How was the work going? Not so far. What would you like to do today? What would be the most helpful thing? Say that again. Discuss some of the exercises. Good job. By now, everybody should have copies of the homework. Right? There's two kinds of homework. One called, I think it's called problems. Right? The other is called project. Problems, project. Normally, in a U.S. class, if somebody uses the name project, they're talking about something big. You know, that would take a couple, maybe a longer period of time. And problem is more like something maybe you do every night. Okay, class has started, so there should be only one person talking. Okay, just one. So, all right. So I'm happy to go over a couple of the projects or problems, at least discuss them. Maybe I'm not going to do them line by line. You know, that's for you to learn. But if you need some guidance to help you start it, that would be fine. Before we start that, though, let me ask: how many finished all of the problem homework? Is it homework number 3? There were 3. I can't remember what they were called. Chapter 3, Chapter 4. Right? So who finished Chapter 3? Nobody? Finished Chapter 3, yeah. Well, okay, so Chapter 2. Who did all of the exercises from Chapter 2? Remember, there's 3 sets. There are exercises. There's problems, or maybe it's called homework. I'm sorry, I don't remember the names. By the way, I know I've told you this a couple of times, but Mrs. Ha has a copy of everything that's in this course on the CD. Yeah, I asked her several times to make sure that you could have a copy. I don't think you got it yet, right? But I encourage you to go tell her you've got to have that copy. Because I would be happy to keep emailing you these things, but my internet connection is very unreliable. So, for instance, I got home this morning and I don't have internet in my apartment. So I can't do anything to help you. So you have to get that disk from Mrs. Haas so that you can have it. Okay? Those homework that I sent you over the weekend, I mean, this is crazy, but I was at a conference in Da Nang. The hotel in Da Nang had a good internet connection. So finally I could download that and send it to you. But I can't go to Da Nang every day and send you the homework. And my internet connection here is not reliable. So you have to get that copy, I hope, from Mrs. Ha. She's got it. She's had it for months. So she's had it for a long time. It's on one CD. I think if one person can get it, then maybe you can share it around or something like that. Okay? But there's 3 different sets. One is called exercises, one problems, and one called projects. So this one, this is practice. I'm not going to take it from you. I'm not going to grade it. Right? This is just for you to make sure you know what you're doing. And that's why the exercise is always put at the end of each lecture so that you can check to see if that makes sense. Right? These 2 are supposed to be graded. You're supposed to turn these in to me, and I'm supposed to grade them. I might not take all of them. Yeah, maybe I'll decide later that we're not going to grade all of them. Maybe it's too much. Okay, but that's the idea anyway. So, my question again, just to repeat my question. How many of you finished all of the exercises for Chapter 2? Yeah. 9 has. Anybody else? 10? Sorry, 10 has. I'm really working on my idea. Actually, I was was successful in Danang a couple of times. I'm really happy. Sin Chao Doi, Wat Cafe Tu Da. I said, okay. And I actually got it. I got what I asked for. It was amazing. Because usually some people have no idea what I'm saying. I know my Vietnamese is good. Sin Chao Doi, Wat Cafe Tu Da. Okay. Do you understand what I said? Tu Da. Yeah, Tu Da. Milk and ice. Yeah. Tu Da. Yeah. Yeah. Sin Chao Doi, Wat Chai Bia. Lot lonely anyway. Okay, done. Yeah. Okay. So anyway, sorry. So I'm doing my exercises in Vietnamese. I'm trying. So are you doing your exercises in C++? Right, so you have chapter 2 so far. There's 3, there's 4, and there's 5. So if you think about all of this put together, it's like having a total of 12 sets. Okay, I think right now, what I think isn't necessarily true, but I think you should be finished with this. You should be finished with this. Maybe about half finished with this. Nothing yet. Okay? Now, I know that on the weekend you got, no, you already had these, right? So I guess this is my question. Are you finished and finished? These 2 you just got. These 2 you also just got, I think. Right? Everybody has these? Okay, so how are we doing? One thing that's true in general about, computing in general is, in our curriculum, normally after the students take this class, every engineering class afterwards, you will have some assignments that you have to write programs for. Because real engineering, normally the calculations are complicated. You can't just do them by hand, so you have to use a computer. So the whole idea with this class is to get ready to write programs. So I say that because I think at the end of this course, even if you're not perfect, as long as you know enough to always look and see what you could do next time, then when you use it in heat transfer, when you use it in fluid mechanics, when you use it in control systems, when you use it in material science, you'll get more and more practice for the rest of your life. And pretty soon you'll be a very good programmer. So I have confidence in you. Have confidence in yourself. That's the good news. The bad news is we still need to get to here. Okay, so where are we? Right now we're somewhere sort of in here, I think. But let me back up a minute. Does anybody have any question from chapter 2, any of these 3 parts? Yeah, homework 3 I think has some things from C++. So, yeah. So I know that you've only had that now for about 2 days or so, right? But maybe you have questions already. I'm sure some of you are already trying to finish. Yeah, so I'm happy. I'm also open for suggestion as to how you want to use the time that we're together. One thing is that we keep going through the lectures together, but the lectures, you have copies of the PowerPoint. You also have the narration, right? You can turn the sound on when you're listening to it. So maybe you don't really need for me to do the same thing in here. Maybe you'd rather ask me a different question or something like that. That's fine with me. Okay, whatever you want is fine with me. Yes?
I have a question on freedom.
Okay.
And
Can you put that up? Problem 3, homework 2. Yeah, this starts with I equal to 1, and it does this as long as I is less than or equal to 3.
So I at the end must be 3.
It'll pass through until on the 4th, until this fails. So it'll go through 4 times. Yeah. Every time this condition is successful, it goes back to here. So the first time through, right, actually, where does it change I?
Plus I over there.
This one here?
Yeah.
That's plus 1, right? That's 4. Oh, plus I. I'm sorry, you're right. Yeah, sorry. Yeah, so yeah, I should go through 3 times. Because the first time through, I is 2. This is successful. The next time through, I becomes 3. This is still successful. Then it goes again. Then when I is equal to 4, that's when this fails. But it won't get to this test until it already passed at this point. So it should pass through 3 times. It will pass through 3 times, and the value of I will be 2, 3, and 4 on each pass.
And is always goes 3 times. But the value of I at the end, should it be used because the usually operators is before I is equal to I plus 1.
Well, when it gets to this point where it fails, the value of I will be 4. So watch my hand while I say the value of I. Okay? I equals 1. I equals 2. Successful. I is less than or equal to 3. True. I equals 3. Successful. I is less than or equal to 3. I equals 4. Not true. Not successful. I is not less than or equal to 3. Now it goes with I equal to 4. Okay. I don't really like this logic personally. To me, this is sort of backwards. There's a word. Have you ever heard this word in English? It's not such a common word, except for engineers use it a lot. Convoluted. Have you ever heard that? Convoluted means that it might be true, but the logic behind it is sort of silly. Okay, that's convoluted logic. So for me, this kind of structure here is sort of convoluted, where you check the condition at the end, and in the cycle in which the condition actually fails, you still go through. It's only after you detect the failure that you move out. But by the time you detect the failure, it already did this part. So for me personally, I'd rather have the condition at the top of the loop. And if it fails, then you don't do what follows. If it fails, you just skip down. And you only do the statements if it's successful. But here, it can go through this part of the loop and reach this condition and find out it's unsuccessful. But it already did this. So to me, that's convoluted. That's my opinion, though. It works. This works. I just don't like the logic. It's kind of like having 2 negatives in a sentence. So I could say, I'm not a man. Okay? If I'm not a man, I'm a woman. If I'm not a man, I'm a man. But that's silly to say I'm not a man. Why don't I just say I'm a man? Right? So that's an example of convoluted logic. It's true logic, but it's silly logic. Yeah. Okay. Did you have anything? Okay.
So we have what from read to sleep. So how we explain or just read out?
Yeah, just make a Word document. think you should, for all of your homework, you should prepare a Word document. You can do a screen capture of this, or just import the text file and insert it in the Word document if you need to put the logic. And you should also be able to do a screen capture of the C out screen. Yeah. Just like in the lecture notes, right? There's always a copy of the C output screen in the lecture notes, and you can just paste that in your Word document. I think it's good practice too for you to improve your ability inside of Microsoft Word. If you already know how to capture the C output screen and put it into Microsoft Word, that's good. So if you already know how to do it, it's not difficult, just do it. If you don't know how to do that, this is an excellent time to learn how to do it, because that's very useful to know how to do it. Okay. Number 2, problem 6. Okay, can we get that now? Okay. Okay, look, please everybody quiet. One. Okay, sorry, just a second. Guys. Okay. Or outside is okay too. You're welcome. Okay. What's different again? Yeah, I'm not sure that I understand the question. I'm not sure. But I think what you're asking is this change the value of vector back here? Is that what you're asking? Yeah? Well, what do you think? Yeah, it should pass by reference, so it should change it both. Yeah, so let's start up here. So this makes x equal to 12, right? Y is 3 and n is 4. What's the result of this statement? Well, this is a different variable, but x star. What's x star? Guys, I can't hear her, okay? Maybe you're interested in her question also, so let's listen. Okay. Yes. So this statement over here, plus y, increases to 4, right? So that's 4 divided by 4, so that would be 1. And what's star equal? What does that operate? Still 12? Are you sure? Star equals that remainder function, right? That we looked at last time?
Percent.
Oh, percentage remainder. Yeah, what is this function?
X.
X x times this. Yeah, okay, so it's still 12, okay? So you print output here and it's 12. Right? Okay, then it pauses. Now where does it even call? Where's the void? Oh, here's void up here, I'm sorry. So it calls void within an x. So reference. And down here it changes x. So x here should be set equal to 12 divided by n plus plus, which would be, we change n afterwards. Right? So 12 divided by 4 would be 3. Then n becomes 4.
So, I mean, what happens if the function of x equal, I mean, for example, if x equal times y divided by n, not y, not plus y, I mean, so what happens if x is different from 12, and which x will we take to the function?
So you're asking what happens if we had a different start value, correct? What start value would you like? Let's try one.
For example, we have got number 10.
Okay, let's try 10. So what's the result of this statement if x is equal to 10?
No, not that. I mean, it's the function of x different. So the value is different. For example, x equal x times y divided by n, not y plus b.
Take the plus plus away? Yeah, so what is y divided by n?
About 0.
0.75.
So x would be equal to 0.
X should be equal then to 9, I think. Right, this is function. If x is 12, plus plus y over n, oh, I'm sorry, that's still 1, but take the plus plus away, y over n is 0.75.
No, but it is integer, so it must be 0.
But x is not an integer, right? X is doubled.
But when we take y divided by n, it would be 0.
I don't think so, but are you sure about that?
Because the condition here integer, so integer divided by integer, it can be another integer, it can be a double or something like that.
But x is double, so I think that this operation, even though n enters into that operation as if it's an integer, because this is an assignment statement for a double, I think everything on the right-hand side is treated as if it's double for the calculation. It would be the other way around if it said n equals x over y. Everything on the right-hand side would get treated like an integer. Okay. I'm not sure I'm answering your question. Maybe you could start a C++, the executable program. Open the C++. Let's experiment together. Can you just copy one of the easy ones from like one of the examples from chapter 2, just so it has the beginning and the end language. Yeah, average is okay. Try average. I think that's fine. Okay. So let's come in here and make int n equals 4 somewhere in here. After semicolon. N equals int n equals 4. Yeah, int n equals 4. Yeah, int. Actually, let's put a space. Let's make 2 integer variables, okay? Take the 4 off. Let's call it I, comma, j, comma, k. Yeah, k. Let's make 3. I don't know if we really need them. Okay, so we've got k equal to 4. Then on this one, let's make I equal 3. Yeah. Okay, good enough. So down here somewhere, after this statement, we'll do a carriage return. Okay. Let's say j equals I divided by k. So, for C output, take AVE out of there and put J. Just right here, J. So we can see what J is. Yeah. Okay, J. Okay, let's run it. Now, oh, I think maybe the declaration needs to go up here. So copy this, put it up here. Cut. Yeah. Maybe that's all. Maybe that was the only problem. Okay, so I think that's 0, right? Okay, so I'm doing the experiments with you to hopefully figure out the question. All right, so let's see what we did so far. We made up some integer variables, 3 and 4. So I just tried doing J is equal to 3 divided by 4 in integers. The J is an integer. The answer comes out 0. Okay? Now let's put in here AVE right after here. Space. Okay, there's one. AVE equals I divided by K. Now let's put AVE. Okay. Can you read that? Is that 0 again? Yeah, okay, so it does use the integer variables on the right-hand side. That's interesting.
So it doesn't mean that the assignment is the same?
Yeah, I thought, to be honest, I thought the assignment on the left meant that this calculation gets carried out as if all the numbers were that way. But this experiment says that's not true. The average came out to be 0. So let's try one more. Let's put, let's make AVE equal to A divided by K right here. Just take the I. Yeah, A. Okay. Do it again now. Okay, so that's also interesting. So this is different. So we have a mix on the right-hand side. You have real here, double here, divided by an integer, and it calculated the answer correctly as a double. Okay, now let's go back and look at the one more question and see if we can figure out. Everybody see what happened there? We just checked 3 cases. One case was we took an integer and we set it equal to an integer divided by an integer. The 2 integers on the right-hand side were 3 and 4. The answer is 0. That's totally predictable. They were all supposed to be integers. Yeah.
I have a question so that it does matter if we put something behind or change one of the. I mean that if the x star equal to x times with the plus y over n and x star equals to plus y over n times 2x. That's different.
If you put times x on the end of it. Yeah, then if you put it, I think, yeah, that's an interesting question. We didn't try flipping the order, so we could go back and try that again, I guess. But when we had, in the tests that we just did, we put an integer equals integer over integer. And this gave an answer that was definitely an integer. Then we did one where we had double equals integer over integer. And this also gave an answer that was integer. Then we did one where we had double equals double over integer. And this gave an answer that was double. Okay, so I think if I answer your question, you're wondering, what if we swap the order here? If the integer came first and then the double, would this be an integer? I don't know. Yeah, let's try. Different languages handle the way. This is an example of default. I used that word before. is such an important word in computers. Default is what happens if you don't say anything. Right? What does the computer think you mean if you don't tell it exactly? So in this case, if we calculate integer over integer, the computer thinks we mean integer. If we calculate integer over integer, it thinks we mean integer, even though on the left-hand side we had a double variable. Right? So the default of this kind of calculation is apparently integer. The default of this calculation apparently is double. So I don't know if we switch it. I'm not that familiar with the defaults in C++. One reason why I'm not familiar with defaults in C++ is that it's usually a much better idea if you say exactly what you want. And don't assume that you have the default correct. Right? Put it in there the way that you need for it to be put in there. Okay? But let's try it out. So I think what we want to do now is let's put K over A here. This might not be a good test because this is bigger than 1. So let's put K over C. Yeah, okay. Yeah, so we got double, right? So when we had a statement that looked like double equals integer over double, this gave us double. I don't know if we've run enough tests now to finally go back and let's answer your question. Try it. Okay. Let's see if we did enough. So let's look back at that more beside the sheet. Okay, so what's the result of this statement? We had integer divided by integer. Y and n are both integers. So the result of this is an integer for sure. That's 1. So this is 12. X is equal to itself times 1 is an integer. Okay? What if X was 10? This would still be 10. Because the right-hand side happens to be 1 in this case. But I think if we change this to 2, if you change Y to 2, this statement would give 0. Because the ratio of plus Y over n, which are both integers, if Y started out as 2, plus Y would only be 3. 3 over 4 is 0. It's an integer. Well, for this statement, we have X equals 12, but if the pluses weren't there, X is equal to 0. Right? Yeah, if there's no plus there, yeah, I think the output for that is 0.
So actually
I didn't understand the last part. Say it again.
when x equals 0 and from the result, it will return to the main program.
Yes, whatever X is down here, it will return because it's being sent by reference.
So x is the function solution. X equals n divided by n plus x is equal to 0 and
Okay, down here we put, according to the experiment we just did, let's suppose that X is 12 at the time it goes down, and N is 4 at the time it goes down. This calculation of 12 over 4, it's a double over an integer, so the answer should be a double, and it would be 3. Right? Then N gets changed to 4. That's this plus. Then here N gets changed to 5. So what should come out of there is 12 and 5. I'm sorry, 4, 4, and 5.
if x equals 0, not in the result x equals x times y divided by n, and the result is 0.
Yeah, if this is 0, then this will stay 0. X equals 0 divided by n plus 0. But n would still be changed to 5. It gets changed to 4 here and then 5. Okay? But x would now be 0 up here. Okay. Yeah, as I mentioned before a couple times, I know sometimes I repeat myself, but usually if I repeat myself, it's because I think it's really important. The calling by reference is one of those really dangerous things. It's useful because you want to transfer the numbers down into the subroutine, and maybe you do want to change the value of the subroutine. But if you're calling by reference, when they come back to the main program, they have new values. So you have to be sure that you're doing what you intend to do. So sometimes it's safer not to call by reference, or to take the variable that you want to send to the subroutine and put in one more equals here and just make up some dummy name, a second name for the same thing, and send the second name down here. So even if it gets changed in a way you didn't mean to happen, the original variable up here still has the original value. So I could say, just before this statement, I could say x equal to x dummy, let's say, a new name, right? Or actually I want to say x dummy is equal to x. And then when I call the void subroutine, I put the name x dummy. That way the thing that gets transferred is not x. X dummy is what gets. And then if something happens down here to x dummy, it doesn't matter up here to x, because I didn't change the value of that. I only changed the value of x dummy. Do you understand what I mean? Yeah, that's the other thing. So just don't call by reference, so it won't affect the main program. Yeah. Did you understand the question better than I did? Okay. Okay, other questions from chapter 2?
One more question is the array. When we put an array on the one tab, with the square array, and then when we have to put the n value and the symbol there, because the n symbol shows that when we put the one function at the end, it will come back to that.
Yeah.
But in the array,
Yeah, you can, in theory, passing back and forth by reference array values should work as well as passing a single value. But if you're not careful with the dimensions on the array, you could end up with something in the wrong position. I don't know if I answered your question, but let's say you have an array, maybe you have x, and it's supposed to be an array that's 6 by 2. Okay? So this is a total of 12. So that's 12 transitions. Under certain circumstances, which are never good for you, you might have in the void function, you might have x by mistake, say, set up as 4 over 3. So this is still 12 positions. So if you call the void function from the main program and you try to pass x, this command might be successful, but it's probably not what you meant, because you probably meant for x to be 6 by 2. In the void function, it's going to appear to be 4 by 3. So where does it put, how do these 12 numbers end up in these 12 positions? That's something you probably didn't plan. So it probably means you made a mistake somewhere, if you do it like this. But as long as you've got 6 by 2 down here, there's no reason not to pass the array, no problem. Okay. Now something that's really easy to do, of course, is this. It's really easy to get in a hurry and not pay attention. And so it's 6 by 2 up here and it becomes 2 by 6 down here. Just because you didn't write it, you didn't write what you meant to write. I don't know if I'm answering the question or... That's not it, okay.
My question is,
write it up there so everybody can see. What's the easiest way to do this?
What functions with that? Yeah.
Now that.
I don't know what the N symbol is. Basically, do the loops of case.
Yeah, the END. Did you run this? Yeah, the semicolon. Yeah, okay, sorry. Yeah. Yeah. I'll have to think about this one. Maybe if you don't mind, send me an email, and I can think about it. We can talk tomorrow. I'll bring it back because I'd like to share the answer with everybody. So I'll make up a file, and then we can project it. Okay. Send me the one that you think shouldn't work, but it does work. Let's see if we can figure out why. Okay. What else would you like to discuss? Okay. Lecture example from, is it one that Alex has? Sine series? Sine series. Okay. Yeah, let's go step by step and evaluate algebraically what the language is saying. So we want to come down to where's the next step? Calculate's the next step. So this one right here. You want to interpret the statement? Okay. The next term then is minus. Next term. I'm going to write it first. Next term. Star equals. And then minus x times x. Then 4 times n times n. Plus 2 times n. Okay. What is this part? What is that? Well, it is, 4n squared plus 2n, but this is the next part of the factorial, right? So let's see where that begins. We had, we start with n equals 1. So when we get to here, the denominator is 4 times n squared plus 2 times n for the next term. Right? So, that doesn't sound right. That's one ahead. Isn't it one ahead? So as it goes through the series, I think this is the denominators. At minus x times x. So we start off with x being our cosine is -1. Right, so x is pi. Yeah, so we're trying to construct a series that the sine of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. This is the series that we're constructing. So we start with the sine of x equal to x. That's here. The sine is equal to x. Then the next term we have as the denominator 6. This has as the denominator 5 times 4, 20 times 6. This is 120, right? But the multiplier here is 20. The next term we'll have, I don't know what that number is, but the multiplier here is 42. So 42 times 120, whatever that is. The next term, right, this will be this one times 72. Okay, so this denominator part of this is saying if I take the last term in the series and I multiply the old denominator by this, I get the correct new denominator. So the first term in the series has a denominator of 1. The second term in the denominator has a second term in the series has a denominator of 6. When n equals 1, multiply the old denominator by 6. The third term in the series has a denominator of 20 times now. So when I go to construct this third term, make the denominator 20 times. Okay? So that's the denominator part. Does that make sense? And the numerator part goes up by x squared, x squared, x squared, every time x squared. So, except the sign changes, right? So this is x, minus x squared to give me minus x cubed, minus x squared to become plus, minus x squared to become minus, and so on. So each new term in the series is the old term, right? This means take the old one and multiply it by minus x squared in the numerator. And in the denominator, whatever this factor is. So the first time it will be 6, the next time 20. That's how it's adding one term at a time. Does that make sense?
So this is the next one for sine function. So what about different?
Yeah, a different function will have a different series. You have to make up a different part of this. For instance, cosine. What's the cosine function? What's the cosine series? Cosine of x is x. That's equal to 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial. So if you wanted to calculate the cosine series, you could have a similar logic, but the algebra would have to look a little bit different. The numerator should be the same. Every term is different by minus x squared. But the denominator, between the first two, the difference is 2. Between these two, the difference is 12. Yeah, 4 times 3. Between these two, the difference is 30. So you need to construct a denominator that would have this, that would look like when n equals 1, this is 2. When n equals 12, and n equals 3, this is 30, and so forth. Okay. Well, I don't have too many series memorized in my head, but you could get math tables that are full of series that represent different functions. So this is one that I know. This is the sine series. I know what this one is. I know what the cosine series is. I can do the exponential, right? What's e to the x? Say that again. Yeah, absolutely. That's exactly what it means. Yeah. I don't know if anybody else can hear a question. The question is, do you need to translate first into the math and then programs the math? Yes. Except a lot of people have used some series so often that they made them a part of the program that's built in now. So for instance, sine. A lot of people use the sine, so you don't have to do it anymore. Somebody built it into the program. A lot of people use cosine. You don't have to do that. It's built into the program. But you could work on a problem in your career, many problems in your career, where you need a function that's important for your problem, but nobody else really did it before, so you have to do it. Yeah, that definitely can happen. Yeah, that's exactly right. Yeah. Everybody hear that question? This is a great question. I mean, this is the whole basis of modern science as we know it. Somebody like Newton comes along. Right? The question has to do with. I'm going to use my words. I'm not saying these are exactly your words, but I think this is the concept. So the question is, who makes up the math problem? Who makes up the math solution? Where does all this come from? And the answer is somebody who's very, very clever and really observes the world, notices something about the world. Like in Newton's case, he noticed that this was true. So now this is the problem. Where did this problem come from? He made it up. He's the one that noticed this problem. Nobody came to him and said, "Can you solve this problem?" Nobody knew that this was the problem. So his first stroke of genius was just the fact that he said, "Oh, here's the problem. This is it. Now what is it?" He needs to solve it, or somebody needs to solve it. So first he published papers. We talked about journals. First he published papers that had this problem. He told the rest of the world, "Guess what? I discovered this is the problem." Now somebody solved it. Then he also tried to solve it. So his second genius was he figured out how to solve it. That's a completely different genius from the first genius, which was to figure out, hey, this is actually a problem. In the meantime, Leibniz, as we talked about the other day in Germany, he saw from Newton that this was the problem. So he started thinking about, how do I solve this? So his genius was only to solve the problem. His genius wasn't to discover the problem. But in your careers, I hope all of you have both of these kinds of genius at some time. You'll discover what the problem is. Oh, that's the problem. And like I said in the other class, in the 140 class, I tried to say this over and over again in those exercises where I ask you to invent the things that you're going to do to change the world. That's the whole idea. Is you're going to figure out what is the problem. Figuring out what the problem is that somebody should solve, I think is more difficult. Then once you know what the problem is, figuring out how to solve the problem might also be really difficult. Right? That can also be a really difficult part. So in this class, we're mostly talking about how to solve the problem, not how to discover what it is. So most of the time you will be given the problem. It's up to you to figure out how to solve it. But you don't have to figure out what the problem is. Mike? my philosophical opinion about the way that most universities teach engineering, I think it's guilty at our university, I think also TNUT and most universities, is they can give students the idea that everybody knows what the problem is. All you have to do is solve the problem. Not true. The biggest challenge is to figure out what the problem is, not how to solve it. Somebody will figure out how to solve it, but you got to figure out what it is that you're trying to solve. It's like I said about the cars. If you stand on the side of the road and watch the cars go by, they're all different. Why? The problem sounds like it should be the same. Build a car. If I want to make money, build the best car. Okay, no problem. Build the best car, solve that. Well, there's trillions of dollars at stake. Quadrillion, peta-BNB at stake for all the cars in the world. Believe me, people want to solve that problem. But nobody knows how to write the problem so that it only has one solution. It has lots of solutions. Big car, little car, high power, low power, aircon, radio. There's a lot of different solutions because the problem isn't a single easy problem. So I got a little bit off on a tangent. But back to your original question about these series. So he's showing you here, he's showing you how to set up logic with one statement that enables you to calculate each term in this series so that you can see if the sign converges. That's great. This is a great example of very good programming. But he had to know that this was the series before he could start to solve it. And so that's also going to be your problem in the future. How do you know what it is that you're supposed to be programming? In this class, it's going to be easy because I'm going to tell you, you have to program this. But usually in your career, you'll have to figure out what it is to write a program. Okay? And I'll do a simpler example than the cars. You know, there are stock exchanges all over the world where anyone can invest. Right? You can buy stocks in every country if you want to buy a piece of a private company. And the stock price goes up and down and up and down and up and down. If you buy the right stock, you can get very rich. If you buy the wrong stock, you can lose all your money. Again, everybody in the world would like to have the right answer. But nobody really knows exactly how to write the equation. If they knew how to do that, everybody would be rich. They don't know how to do it. And believe me, people are trying. Really smart people, PhDs in mathematics, are trying every single day to figure out how to do this with the stock market to make themselves rich. It turns out, so far, nobody really knows how to predict very well. Some guys, they do really well for a while, they get kind of rich, but then they usually get confident and lose all the money sooner or later. Okay. So one other thing about the programming. As far as programming a series like this is really clever because it uses each term as the basis to calculate the next term. But if you were writing this program, you might scratch your head and think hard and try to figure this out. It's so complicated to figure out this expression. You could spend 2 weeks figuring out this expression, and maybe in 2 hours or 5 minutes, you could just write a do loop that has all of these expressions in it. It would not be as elegant. You would have more lines of code. But you don't have to figure out ahead of time that this is the correct expression for how the denominator changes so that you can multiply each term by the last term. Right? This is very clever. Whoever did this is very clever. But it's not necessary. You can calculate this term, this term, this term. Just calculate it. You don't have to write something that fancy. Why don't we do it? Let's do a do like this. Let's do an if. Let's do it as an if. So we'll start off with sine equals x. Sine equals x. This is my function. It's not as clever as that, but it will work. So, okay, if sine divided by x. Let me put it in there. If 0.999, let's say 999, is less than or equal to sine divided by x is less than or equal to 1.000. Return. Because if this is true, then I already have the sine I'm already down to 1/1000th on the sine. If the sine is actually equal to x, it means I don't need the next terms. The first term is sin x equals x. Okay? Now, if that's not accurate enough, if 3/9 isn't enough for you, then 4, 5, no problem, whatever you want. Right? If that's true, you're done. You have the sine. If that's not true, and actually, we don't even need the f, right? Else. Well, let's go ahead and do it. Well, no, let's do it. Else, we can add sine is equal to sine minus x power x3 slash. And is it called factorial? Does anybody know? Anybody know the name of the factorial function? It's FAC? Yeah, for the factorial. Is it FAC? It's probably FAC. I don't know. Yeah. Okay. So if this is, so if this is true, if it's not true, add the next term. Then the same kind of thing. Put this back down here. Just copy it. So then it has if. I'm writing it less. I'm writing math. I should be writing this way. And if that's true, then return. And otherwise, inside of this, I think I need to work on the logical of this, but you see what I'm doing. So I can check after each term. I can write each term out longhand like that. Add it to the sign. The next one will be plus, right? Power x5 over fact 5. It's not as clear as this. It's not as elegant, but it works fine. So you're just doing the exact same logic. And then just keep going until this condition is satisfied. When this condition is satisfied, done. Okay? For the real computer geeks, everybody know this word? It's a good word. What are geeks? What are geeks? Anybody know what a geek is? This is a great English word to know. If you ever show up on a campus in the United States, you want to know what this word means. Geek. Who's a geek? A geek is usually somebody who's pretty smart, but is totally not cool. Yeah. So they probably don't really like him very much, doesn't have a girlfriend, doesn't know how to dance, something like that. But he's pretty smart, he's pretty good at that, Okay, so for the real geeks, for computer geeks, they often have programming competitions. And usually the competition is, you have to make some complicated calculation using the minimum number of commands. So whoever can do it with the least number of commands wins. So they're the kind of people that spend all night trying to figure out one statement like this that calculates the next term. For normal people, you can just do it one at a time, no problem. It'll take a few more lines. Your program will look a little bit longer, but it will calculate the exact same thing. So I think it's not really a good use of your time to worry about getting something like this. But since we have it, since he gave it to us, we can admire it. This is very clever. This is one expression that calculates the next term in the series using the last term in the series. So it's very efficient. But this will still give you the same answer. Yeah, in fact, this might even be more accurate. The reason why this might be more accurate is what? Why do I think this could be more accurate than this? If I go, let's say we had 5 terms in the series before we finally converged on the sign. So we either calculate this 5 times, or one at a time, we call a statement like this. The next one would look like POWX5/fact5. Why do I think this will be more accurate? Because of round-off truncation error, remember? So when we calculate the first term in the series, when that term gets stored, it gets truncated, 12 digits. So it's not perfect. If we calculate the next term using what got stored as the starting point, we start with a number that's not perfect. Then that number gets stored. Then the next term uses that as the starting point. So maybe after 5 times, this number is starting to not be very accurate anymore, because each time we're starting with one that's not right. This one, we start from scratch using these functions. Each time we start off perfect, and the next term might have a little bit of error, but it doesn't pass on to the next term. It's just one term at a time has a little bit of error. So if the series has a lot of terms, this will be more accurate than this, even though this is pretty good. Okay. Yeah, geek. Do you know this word? Nerd? Yeah, nerd means basically the same thing. Geek and nerd. There's a famous movie. It's a college movie in the U.S. It's called Revenge of the Nerds. Have you ever heard of that movie? Okay, so the basic story is that there's some guys on the campus, and they're nerds. They're smart guys, but they're kind of annoying. Nobody likes them. They don't have any girlfriends or anything like that. And there's some cool guys on the campus. And the cool guys have all the girls, and they dress nice, and they've got cars and so on. And so the cool guys are always doing mean stuff to the nerds, because the nerds are sort of weak and quiet. They can get away with it, so they pick on them like boys. Finally, the nerds decide, no way, we're not going to do this anymore. So you know what revenge? You know the word revenge? Yeah, it's when you get back at somebody. So the nerds get back at the cool guys. So they do it by being brilliant. They make all kinds of special devices, traps, booby traps, stuff like that. So even though they're not as strong, they're not as clever, well, they're not as strong, not as athletic as the cool guys, they still end up winning because they're smart. And so they can make all this stuff. So the movie is called Revenge of the Nerds. It's a good movie for engineers, because most engineers, it's famous in the United States that engineers are usually nerds, because they're smart, but they're not very cool. Okay, so I got a joke for you. Maybe you can get this, maybe you won't get it. See if you like this one. So there's an engineering student who's a geek or a nerd. He's sitting in his room one night. He's working on the computer. Always on the computer, always doing some programming like that. And all of a sudden, the frog pops up onto the windowsill. And the frog says, "Help me, help me." And the engineer doesn't even look. He just keeps typing. And so then the frog says, "Please, you have to help me, you have to help me." And the engineer just keeps typing. And then the frog says, I'm a beautiful princess. Princess, yeah. I'm a beautiful princess. And an evil wizard turned me into a frog. And if you kiss me, I become beautiful again. And the engineer just keeps typing and typing. And so then she says, "My father's a king. He's very, very rich. If you kiss me and turn me back into a princess, I'll marry you. You could become the prince. You'll be king someday. And I'll be your wife. You can do whatever you want. I'm very beautiful. You have to help me." And he just keeps typing. And finally she says, "Why won't you help me?" And so he opens the drawer of his desk. He takes the frog. He puts it in the drawer and he shuts the drawer. And she says, help me, why won't you help me?" And he says, "Look, I'm an engineer. I'm really busy. I don't have time for a girlfriend." Yeah, but a talking frog, that's pretty cool. So anyway, that's a geek joke. So if you don't understand a geek is a guy who would rather have a talking frog than a girlfriend. computers. So what other question would you like to ask? Yes? Okay, so start over, please. Which problem? Number 2? Oh, project 2. I'm sorry. Okay, sorry. Yeah, Alex, we put project 2. Yeah. Stuck here. Sand. Oh, I got 11:30. That's not good. Yeah, cannonball problem. Good. EAS 208. See, as I said before, normally the engineering classes that follow this class will use something from this class to write programs, so it gives more and more practice. All right, but this one goes backwards. It uses 208. So good. All right. So do all of these numbers look familiar? All of these equations look familiar from 208? Okay, that's good. So D is the distance that the ball is going to travel. A is the angle from the ground that the cannon is pointed. D is the initial velocity. It's not spelled right. That should be initial velocity. That's the starting velocity. Initial, right? Initial means beginning. G is the gravitational constant. Use 9.81 meters per second. T is the time the ball is in the air. H is the maximum height. Okay, so write a C++ program that does the following. Asks the user for the distance of a target. Asks the user for an angle from the horizontal that the cannon is aimed and fired. So that's 2 inputs, distance, angle. Then it calls a void function that calculates the distance traveled, the maximum height reached, and the time traveled for initial velocities of 10, 20, 30, 40. So each of the 3 values, D, H, and T, must be calculated using 3 separate single result functions. Sorry. Okay, this part it sounds like whoever wrote this problem wasn't thinking, because it asks the user to input the distance. But then the program is supposed to calculate the distance using the input angle and these 4 initial velocities. Okay, so that sounds a little bit confusing. Is that the problem?
So we have to both void function and a single function.
I don't know if you have to use the single function, but you can use the single function. But it says use a void function.
But it's all picked up the must be calculated using the separate single function.
Yeah, from the void function.
Yes.
Yeah. And that should come from the void. So inside the void function, you call these 3 other functions. Okay.
3 other functions is a single function.
And they're all single result functions. Yeah.
So if one,
say again?
I do this, but it will work.
Okay.
I don't know.
Maybe you can bring your code, right? You could go through line by line. Did you put output statements through your code so that you can see when the calculation is incorrect? Remember, I recommend that you do something. When you're writing the code, you'll have a regular statement, and then follow immediately with a comment. It look like this. My format, my memory is terrible. I think that's how you start the comment, right? And here you say what that statement is supposed to do. And next you have C out. And now you put here so that you can see what it did. And that way, when you go through the program the first time, line by line, you can just check every line and make sure it calculated what you think. So that way, at least you can figure out which statement it is that's not doing what you think it's supposed to do. Yeah. Okay. Yeah, so I mean, I'm not sure. I don't think you were asking me a question. You're just telling me that the program doesn't work yet. So is there, yeah.
I think we can use the void function and the single function at the same time.
Yeah. Oh, yeah. You can call the single result function from inside the void. From inside the void. You can call the void. You should have at the top of the whole program, you should have the void, void name, right? Single name. So that's at the top of the main. And then you'll have separate sections, at least 4 a void function and 3 simple result functions.
And after I run people 0
Yeah.
and I have a void function.
Yeah.
And after the void function, I have 3 separate single result function below the void function.
Or above, right? The exact location doesn't really matter as long as they're separate. So you'll have the main part of the program. Then you can have the void function next with its own. And below that you can have a single result.
So the result of the single result function can be increase the void.
Yeah. But the other thing I was going to say is anything outside of the main, it doesn't matter what order they're in. So if you want, you can put this one first and then void. That doesn't matter. Yeah.
This is why I go around like this to see 3 single result functions into the void.
Well, the call, you can do the call statement to use the single result function of the void. But the single result has to be outside of the void, right? It's a separate chunk of the program. Main program, function. Yeah, so they have to be separate, but each one has its own return.
I think it's the void function is not
Okay. Yeah, you can do all the reading and writing out of these functions too if you want. It doesn't have to be the main. I mean, maybe he says, the user is supposed to put in a distance. The user is supposed to put in an angle. Well, I don't think it really says that has to happen here. If you want, it's up to you. You could put that here. You could even have another function, another void function. You could call from here, and the only point of that void function is to get the input. Yes, ask again. No, I think you should use 3 single result functions like he asks. Well, no, because I think the point, one of the things that you're supposed to learn from this assignment is to make sure that you understand how to have multiple functions inside of one big program. Okay, that's useful in the long term of your life because you want to have your own libraries of user functions that you can use over and over again in different programs. So it's important to make sure that you understand how to separate them into functions and then call different functions from each other. So if you're having trouble with it, that's the whole point of the assignment, is to help you to learn how to do that. Okay? If you put it all in one main program, then it won't help you to learn how to do that. I think I told you before, but for many years in computers, the only way to put statements into the computer, there was no such thing as a terminal. No such thing as a keyboard. You had those cards, the cards. They're pieces of paper. They were about this big. Each one had one command on it, like this. So if you had a subroutine, it would be a separate set of cards, maybe 50 or 100 pieces of cards to make up a function. And somebody that works on computers a lot, like I did when I was a graduate student, for instance, in my office, on the shelves, I would have boxes full of different cards. Here's the sine function. Here's cosine function. Here's exponent. And if I wanted to put together a program, I would write the main program. That would be one set of cards. Then physically, I do it. Take the cards for the sine, put it on the end. Take the sub cards for the cosine, put it on the end. So end up with this big long program. This is exactly the same logic. Here's your main program. And maybe you want to be able to input-output something. So you write it as a separate. And then if you use a different main program sometime, you can still do the input-output. You don't have to rewrite it. You just take that part and add it on the bottom. If you want to calculate those same equations for some other application, if you have them in a single result function, you can always just take that function and add it to another program. You don't have to rewrite it. That's the idea. By the way, when I taught, the last time I taught 208, when we were doing these kinds of problems with projectile motion, initial velocity and an angle, and then you figure out how far something goes, how high it reaches, right? The general word for that, you probably heard this. This is ballistic. Yeah. Have you ever heard the word ballistic? Ballistic is when all the energy comes in at the beginning, and then after that, it's actually just cruising. There's no new force coming on it. It's not getting new energy. So in my ballistic problem, I thought it would be more fun instead of talking about shooting a cannonball or something like that. My ballistic problem was Tarzan. You know who Tarzan is? Yeah, guy who lived in the jungle, smoking the trees and everything. So Tarzan is in the jungle and he's being chased by pygmies. Pygmies are people who live in the jungle. They're very short, and they're good hunters, and they use poison darts. They blow the dart through a tube, where they have a little arrow they shoot, but they get poison from frogs, and they rub the end of the dart in poison. And if they shoot you with that, it's like a snake bite. The poison will kill you. So in my problem, Tarzan is running through the jungle, and some of these guys are chasing him. If they shoot him, he's going to die. So he's running as hard as he can. And he comes to the edge of a big gorge. So here's some trees. Here's some trees on this side. But this is really deep. I don't know, 1,000 meters. So he's running. Really terrified. And behind him are the little guys. And they've got the poison arrows. If they shoot him, he dies. So he has initial velocity this way. He runs to the edge. If he jumps over and he makes it, he's going to live. If he doesn't jump right, he's going to fall in the hole and he's going to die. So the question is, can you calculate this distance? Call this V. There's a height here. So I'll tell you D, I'll tell you H, I'll tell you V. And you have to decide what angle, alpha, for his initial velocity, what angle should he jump so that he can go up and over and land on the side safely and survive. That's the way I like to ask that question. So it's maybe a little more fun than shooting a cannonball. Okay. Actually, if you watch athletics, something like the Olympics, I mean, those runners, they have the same problem in something like long jump or high jump. Right? They're trying to do this problem. They're trying to do ballistics. Once they push off the ground, they're ballistic. Now they're just sailing. They're just cruising. There's no more energy coming in. How do you get the maximum distance in one case? How do you get the maximum height in the other case? So it's interesting. They're solving a 208 problem. Most of them couldn't do it mathematically. They don't know enough about mathematics like you do. But they train their bodies to try to get a maximum ballistics. Okay, more questions about this? Or are you okay with this? Yeah. Okay. What's next? By the way, on ballistics, as I've said many times, I like aerospace. So I work usually on either airplanes or spacecraft. And it's completely different because most spacecraft, they have a huge energy input in the beginning to get into orbit, and after that, they're ballistic. They just cruise. There's never any more energy. But an airplane has energy coming in the whole time to overcome atmospheric drag and other things. But a spacecraft, the idea of a spacecraft is you have to make the very accurate calculation at the beginning. Here's Earth. Let me try it. Here's Earth. You launch a spacecraft. It looks like it's going up at first, but if you watch it, it always starts to angle over. So it comes up and then it starts to go over to the side. And what finally happens is it ends up perpendicular in a velocity perpendicular to the vector from the center of the Earth. Now it has an acceleration down that's approximately g. G gets smaller the farther away from Earth you get, but it doesn't get small very fast. So it's not correct. When you see pictures of people in space, they always kind of look like they're floating. Actually, they feel the same G you feel right here. So they're not floating. They're falling to Earth at a really high velocity. But they also have a high horizontal velocity. So the total velocity is the sum of these two. And if you get that sum exactly right, then they kind of go in this direction, and they just stay in that general direction the whole time. They're always falling to the Earth. That's why this curve. So they have a big horizontal velocity, but they also have a big vertical velocity. And that keeps them curving. And if you get it just right, they can stay up there for years. We call it orbit. There are tens of thousands of things orbiting the Earth, including the one that brings us television, some of the internet, a lot of cell phones, that go off of satellites. So it's really important to humans to get this right. Parachutist, when he first jumps out of the airplane, he definitely has a horizontal velocity, yeah. But the wind will slow down the horizontal velocity, and finally he'll have most of the vertical velocity. But yeah, when he first jumps out of the airplane, he has the same horizontal velocity as the plane. So in theory, if you could put somebody onto an airplane that was going fast enough and high enough, they could jump out of the airplane and be in orbit without a spaceship. Right? That's possible. It's theoretically possible. How long can you hold your breath? No air. Okay, so as you might guess, the closer you are to Earth, the higher horizontal velocity you need to stay in orbit. So there's a few orbit heights that are very highly used. One is at the edge of the atmosphere. And at the edge of the atmosphere, you need a horizontal velocity that will take you around the Earth in approximately 90 minutes. So there are a lot of satellites that are in orbits that are something like 90 minutes. Those are the ones that usually look at the Earth and they fly over the Earth, like GPS. Then the other one that's really common is at the equator. If the satellite is flying this way, the same way that the Earth rotates, if you go out far enough, the horizontal velocity gets slower and slower, and finally you can get to the exact horizontal velocity so that you don't move relative to the surface of the Earth. So you stay over the same place on Earth forever. Okay, that's called geostationary. Geostationary. This is communications. So if you look outside on the side of a building that has a satellite receiver, right? That satellite receiver just sits there. It's fixed. It's always moving at the same angle from the surface of the Earth. But the Earth is spinning around and flying through space at very high velocity. So how can that thing just keep pointing at the same spot and receive the signal? Because the satellite is up there, also moving with a very high velocity, but the timing is perfect. So the satellite just stays over the same place on Earth all the time. Okay, it's cool. But there's also these lower GPS satellites. This altitude is usually something like 500 km. You can see them. Like, as I mentioned before, if you're in a clear night, it's dark around, you can watch these things go overhead. Most of them, because the orbit is 90 minutes, most of them are designed to fly north to south, or south to north, to go around this way. That way, when they're flying, the Earth spins slowly underneath them. So one pass, they come on one part of the Earth, then 90 minutes later they come back, and they're looking at a new part of the Earth. And how far away is it? How much rotation is 90 minutes? How much rotation is 60 minutes? Yeah, 1 over 24 times 360 degrees, right? Going all the way around the Earth. It's 24 pieces. Yeah, so this is 15. So the sun moves over the Earth at 15 degrees per hour. So these satellites move over the Earth at about 22.5 degrees for each pass. Okay, and we use those to observe the Earth, things like weather, forest, water, floods, temperatures. Because the Earth is spinning underneath, it sees a different part of the Earth every time it comes around. So sooner or later it can see the whole Earth. Whereas the geostationary, it only looks at one place, where your antenna is, so you can watch television. Okay. All right. It's kind of sad. I mean, it's amazing. It's amazing. On the good side, it's amazing that humans know how to do this technology. And on the bad side is we use it for something like MTV or HBO. I think television isn't very good, but we do know how to get television anywhere you want in the world with the satellites. Okay. Other programming questions? I have no idea. Well, I can figure it out. Let's see. I must hit a funny button on watch. It always works until I come to this class. That's mysterious. Somebody in here has an electronic. It's 1440, so. Okay, got it. Do you want more time to keep working on the homework? Should we move ahead? What do you want to do? More time? Yeah. How much? 2 days more? Yeah, we're running low on days, so it would be nice to get to the end of chapter 4 by, I don't know, let's say, by Wednesday. So I think we end chapter 4 by the end of class Wednesday. Then we can do MATLAB on Thursday, Friday, next Monday, next Tuesday. That's 4 days of MATLAB. Yeah. Well, you want to end chapter 4 tomorrow? We can try to end chapter 4 tomorrow. Maybe we'll try to end chapter 4 tomorrow. Okay. I know we did the group finding. We talked a little bit about group finding. We didn't really talk about, I don't think we talked about numerical integration yet, did we? Maybe a little bit. We talked about numerical differentiation. We did linear regression. Yep. And I think we did numerical differentiation. So the idea is very straightforward. dx, say dt, x is a function of time. The dx dt, this is defined, this is math, this is analytical closed form. It's the limit as delta t goes to 0. X at t plus delta t minus x at t divided by delta t. This is straight from calculus. So the idea in your calculus class was to figure out mathematically the closed form expression for this limit. And you could figure out things like Cosine of x, we just did this one. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x6 over 6 factorial. So the sine of x, if you take this expression and you substitute it in and you calculate the actual limit, you'll find that the sine of x is equal to the derivative of the cosine of x dt. And you could go term by term. Right? The 1 would give you 0. The next term would give you minus 2. 2 over 2 is 1, right? So you get x. Yeah, minus, sorry. So the derivative of the cosine is minus the sine. That's x here. This would give you 4 times 4. So that knocks the 4 out of the factorial. And this gives you minus x cubed over 3 factorial. Right? And so on. Then minus plus x5 over 5 factorial. So you can see from the math what the derivative is. That's closed form. But there's a lot of functions in the real world that you can't see what it is. So you just make this calculation as close as you can with delta t as a small number, but it's a real number. So you write a program, you put in delta t, you evaluate the function in t plus delta t, you evaluate the function in t, divided by delta t. Just make this calculation. That's numerical differentiation. Numerical integration, it's the same idea. I know we talked about this a little bit. So numerical integration, if this is, say, x of t, this is t. So the function looks something like this. If this is t1, this is t2, the integral from t1 to t2 of x of t dt. In calculus, analytically, I figure out what this is and I get an equation, closed form. In the computer, numerically, I calculate the integral as this area. How do I do that? I set up a do loop with a lot of pieces. I cut this into little pieces. And for each little piece, I evaluate the height of the piece, and I evaluate the width of the piece. Multiply them together, I get one little piece of area. Inside of the do loop, add all the pieces together, and it gives me the calculated size of the integral. Okay? If you can get an analytical, mathematical integral or derivative, it's better. Because if I know how to calculate this equation, I can evaluate it in T2 and take it and subtract the same thing, evaluate it in T1. And this will always give me the integral. So if I want to know what the integral is for a different T1 or T2, all I have to do is substitute a new number out here. But if I calculate it numerically inside the computer, if I change T1 or T2, I have to start the program all over. It has to do all the little pieces again and add it together. It can't predict what the next integral is going to be because it has no memory. It only knows how to add up the pieces that you tell it. So when you get additional space, it has to calculate all the little pieces. Everybody understand that? So if you can get them in closed form, it's always better. But in a lot of real-world problems, you can't get them in closed form because you don't know what the function is. You collect some data. I send up a satellite, it flies around the Earth, it measures a bunch of temperature. What's the function that describes the temperature around the Earth? I don't know. All I have is a bunch of numbers that I collected from the satellite. So using the numbers, I can make numerical calculations to try to figure out an integral or a derivative. But I can't get an equation for it because I don't know what it is. All I have are the numbers. Okay? Numerical numbers. Numerical differentiation, numerical integration. So that was a big part of what was left in chapter 4, I think. In chapter 4, you'll see on the integration side, if I expand one segment here, so let's say this is t, and here's x of t. this could be the value of t1, and I'm curious, I want to know what is the value of t2, the value of x. So I know x over here, x at t1, and x at t2, I don't know what it is. But I'd like to know what it is for some distance across here. I'll call delta t. So I take x at this point, then calculate the derivative. dx dt evaluated at t1. And let's say that that derivative looks like this slope, right? It's a slope. So based on that derivative, I can believe that the value of x at t2 is going to be this value. This would be a function of x at t1. That's the start point right here. And also the derivative at t1. That's this derivative. But it should also work backwards. So if I take this value of x and I substitute that into the function and calculate the derivative going backwards, if the function is a perfect straight line, it will give me the same derivative going backwards. But if the function has any kind of a curve, like sine or cosine, then the derivative over here will be something a little bit different. So let's say the derivative over here, maybe this is dx dt at t2. Well, based on that derivative, it says that x at t1 should be up here. But I know that's not true because I know x at t1 is down here. So if I shift that derivative down here, it would predict that value. So this is x of t2 here as a function of x at t1 and dx dt at t2. So in both cases, I know the starting point. But in one case, if I assume the slope at this end is correct, it will predict that value. But if I assume the slope at this end is correct, it will predict this value. Okay, which one is right? We don't know. This is our. We're trying to be logical about making a good prediction, but we don't know what is the right answer. So another thing I can do is I can divide the interval in half. So I'm not trying to predict so far. So maybe I predict halfway across to right here. Calculate the slope at that point. The idea being the slope in the middle maybe is about the average slope for the whole distance. So here I have dx dt at t1 plus delta t over 2. That's halfway across. And maybe there I calculate a slope like this. I'm going to try to get one halfway between these two, so that would be about like that. So based on that slope over here, I predict this value of x. Is that right? Who knows? We don't know. That's the point. If we knew the function, we would just calculate it. Because we don't know the function, all we can do is invent ways like this to see how well we might be able to predict the other end. All right, so numerical integration, this is what we're stuck with, numerical integration. Why is this important? Because you want to live through your next airplane ride, or your next car trip, or your next train trip. Anything that moves has this as its basic law. There's the basic equation for anything that moves. And in order to figure out where it's going, I need to calculate x. And that requires me to do 2 integrations. And I might not be able to even do one without relying on something like this. So it's really important to know how to do this well. And that's the numerical integration part of chapter 4. I don't think in 1 or 2 days, or 2 weeks, or 2 months, you're going to become an expert at numerical integration. So that's not the point. The point is that you understand that this is a critically important problem. And it's a big part of why a lot of mechanical engineers do computer programming. Because you're stuck with this problem all the time, over and over again. My satellite flying around the Earth, actually, I don't know F equals ma perfectly for the satellite. Even though I built it and I launched it and it goes up where I think it's supposed to go in space, I can't predict exactly what the inertia is, for instance. As it flies around, sometimes the sun shines on it, it's really hot, it expands a little bit. Okay. I guess there's another class in here. Oh, okay. Sometimes it goes into the shadow, it's cold. Sometimes there's a magnetic flare from the sun. The gravity of the Earth changes. It's not constant all the way around here. You're given a number like this. Actually, that's only an approximation. Some places the Earth has a little more gravity, some places a little bit less gravity. So it's interesting, but it's true. So if I'm trying to predict exactly what my spacecraft is doing, I actually don't know this equation perfectly. So I'm going to have to measure the force as best I can. Integrate 2 times using something like this in order to figure out the position x. And I better get the position right, because otherwise, when I go out on the side of my house and I put my satellite dish there to receive HBO, I won't see anything because I'm not pointing at the right place. So I better be able to know how to do this and point in the right place. That's important. Or something less important, like I'm trying to land an airplane on the end of the runway. Yeah, it's okay. I guess we're out of time here. Yeah. Ooh. Okay, good luck with the projects. We'll see you tomorrow at 1 o'clock. Hopefully you'll be able to send an email. Like I said, my service is very unreliable.